Hi, my name is Priyansh Rawat and I will be discussing about the Heisenberg spin chain system in one dimension. And we are considering n equals to 4 case here, an antiferromagnetic system. So the exchange coupling constant will be positive. Also, I will be formulating the Hamiltonian here at the end with the help of the Python code. So to begin off, first we consider n spin half particle, and since it's an Hilbert space and we have tensor product here, so we can use this formula 2 raised to capital N to calculate the total dimension. And here 2 raised to 4 because n is 4 and we get 16 dimensions. So in order to get the Hamiltonian matrix, first we will start with three Pauli matrices, which are defined like this: sigma x, sigma y, and sigma z. And we will define physical spin operators, which are S alpha, h bar by 2 sigma alpha. And we are taking h bar is equal to 1 for simplicity because it will be helpful when we calculate it further. After that, we will consider the 16 dimension system, and it is defined like this. And there would be 16 possible spin combinations here, as you can see. After this, we will define a new type of product, which is called Kronecker product. And by this visualization, you can see how it works. You can see how it's getting multiplied here and how it's getting duplicated in this whole lattice form. Using this knowledge of Kronecker product, we will define a single site operator. So basically, we have two indices here, Si and alpha, and at ith position, we will keep the S alpha operator here, and we will surround it by the identity operators here, and they are all multiplied by Kronecker product. Now, we also define all these operators here, and using this knowledge, we will define our own Hamiltonian. So Hamiltonian H cap is J into Si plus 1 summation. And you can see there's a dot product here. So we get this whole summation here. Here J is the exchange coupling constant. It will be positive for antiferromagnetic case. And we are considering the bond position. So basically interaction of two adjacent spins are being considered here. So on simplifying, we get this whole expression here. And we will use this expression while calculating the Hamiltonian in Python code. So first we will see the numerical algorithm that is being used here. And this is the algorithm. First we will define the sigma x, sigma y, sigma z. As you can see, I'm setting up here the single site operators using an np.array method. And after that, I'm making the physical spin operators, which is zero point 0.5 into sigma x, sigma y, sigma z. And we have also a constructor here, which is defining the capital N, capital J, and the dimension, which is 16 here. After that, we are also generating the basis table. So 0 is for spin down, 1 is for spin up, just to make it more clear in further calculation. After that, we are considering capital N equals to 4 case here, and we are making d by d zero matrix. So you can see here H is dimension by dimension 0, np dot 0 method is used, and we are considering a 16 by 16 dimension 0 matrix here. After that, I'm using this operator on site method. So we already have a method dot cron here. So we just put the result, which is our operator, inside the ith position. So I will be the site position in there, and there is a cron product between all the matrices here, all the operators here. You can see I'm building the Hamiltonian here. I'm using this formula to first calculate H interaction term, and this is by this formula, and we are just adding it to the main H formula. After that, I'm just printing the whole thing. I'm using a display method which I defined. The whole, since it's a big matrix, so the whole thing is saved in h4.mpy file. And after that, you can see this is the output on the screen. I have dimension 16 by 16, total 256 elements displayed the top left part of that matrix. You can see that there's a heat map kind of diagram of the whole Hamiltonian matrix. Thank you.